Imagine standing at the edge of the ocean at night, staring out into total darkness. You can feel the water beneath your feet. You can hear the waves, but you have absolutely no idea how deep it goes, what's swimming beneath the surface, or what kind of creatures live in the blackness a mile below. That strange mix of wonder and unease. That's exactly how astronomers feel when they look out beyond the familiar plane of our solar system, because above and below us, stretching in every direction into the cosmic dark, lies a universe so layered, so breathtakingly vast, that even the most seasoned scientists are still piecing together what it all means. Most of us grew up with the same mental image of the solar system, a flat diagram on a classroom poster, planets lined up like beads on a string, orbiting around a yellow sun in the center. Neat, orderly, simple. But that image is one of the biggest lies ever printed on school walls. The real solar system is messy, dynamic, layered, and it extends in every direction, including straight up and straight down, in ways that will fundamentally change how you see the night sky tonight. So let's go there. Let's leave the comfortable orbits of the planets behind and travel outward, above, below, and beyond, into the most mysterious regions of our cosmic neighborhood. And trust me, what you're about to discover will make every glance up at the stars feel entirely different. Before we go anywhere, we need to sort out one confusing problem. What do above and below actually mean in space? On Earth, it's obvious. Down is where your feet are. Up is where the sky is. Gravity does all the work of defining those directions for you, pulling relentlessly toward the center of the planet. But the moment you leave Earth's surface, those comfortable definitions start to break down. Astronauts aboard the International Space Station don't have it down in any traditional sense. They float freely, and whether they're oriented with their heads toward Earth or their feet toward Earth, makes no practical difference. Two spacecraft approaching each other from different angles might have completely contradictory ideas about which way is up. One astronaut's above is another's sideways, and neither of them is wrong. So when astronomers talk about what's above or below the solar system, they need to agree on a shared reference point. The one they use is called the ecliptic plane. This is the imaginary flat disk traced out by the orbits of the planets as they travel around the sun. Think of it like a giant vinyl record spinning in space, with the sun sitting in the middle and the planets skating along grooves, cut into the surface at varying distances from the center. This orbital disk isn't a perfect flat sheet. Each planet has a slight tilt relative to the others. Mercury's orbit, for example, is inclined about 7 degrees from the mean plane. Pluto, demoted to dwarf planet status, though it may be, has an even steeper tilt of nearly 17 degrees. And comets are truly the rebels of the solar system, often arriving from impossible angles, slicing through the ecliptic plane like needles, piercing that vinyl record from almost perpendicular directions, completely ignoring the neat orbital conventions followed by the planets. But take the average of all the planetary orbits, and you get the ecliptic plane, and that becomes our cosmic floor. Everything above it we call north in the solar system's reference frame. Everything below it we call south. With that agreed upon, we can start journeying outward into the layers that most people never think about, starting with a structure so enormous and so ancient that it wraps the entire solar system like a ghost you can't see, but whose fingerprints are everywhere. The first and most extraordinary thing that exists above, below, and in every direction around our solar system is one of the most mysterious structures in all of astronomy. Scientists call it the Oort Cloud, and the moment you truly understand its scale, you'll never think about the solar system the same way again. The Oort Cloud is not a flat ring or a disk. It doesn't hug the ecliptic plane like the asteroid belt or the Kuiper belt. Instead, it's a vast, roughly spherical shell of frozen material that completely envelops the solar system on every side, above, below, to the left, to the right, in every direction you could possibly point. It surrounds us, the way an eggshell surrounds a yolk, except this shell is unimaginably enormous. To appreciate its scale, you need to start with a unit that astronomers use as a measuring stick for the solar system, the astronomical unit, or O. 1 O is the average distance from Earth to the Sun, about 150 million kilometers. It takes light roughly 8 minutes to cross that distance. The outer planets are tens of O from the Sun. Pluto orbits at an average of about 40 astronomical units. The Voyager probes, the most distant human-made objects ever launched, are currently somewhere around 160 to 200 astronomical units from the Sun after more than 4 decades of travel. The Oort Cloud is thought to begin somewhere around 2000 O from the Sun and extend outward to somewhere between 50,000 and possibly 200,000. Oh, that outer edge is roughly a quarter to halfway to the nearest star, Proxima Centauri. When you visualize the familiar solar system, the planets, the asteroid belt, even the distant Kuiper belt, as a single small dot in the center, the Oort Cloud is the massive, diffuse halo surrounding that dot. In every direction for a distance almost incomprehensibly larger than the dot itself. And what is the Oort Cloud made of? Trillions upon trillions of small frozen bodies, icy chunks of rock, frozen water, methane, ammonia, and carbon monoxide, ranging in size from small boulders to objects potentially rivaling the dwarf planets in scale. These are the leftovers, the raw debris that wasn't incorporated into the planets or the inner solar system during the chaotic period of planetary formation about 4.5 billion years ago. Here's how astronomers believe it formed, and it's a story involving some of the most dramatic gravitational pinball imaginable. Early in the solar system's history, the region around the giant planets, Jupiter, Saturn, Uranus, and Neptune, was crowded with countless small, icy bodies jostling for position. As the gas giants grew massive and settled into their final orbits, their enormous gravitational fields acted like cosmic catapults, flinging these icy bodies outward with tremendous force. Some were ejected from the solar system entirely, vanishing into interstellar space forever. But many others were hurled to enormous distances, and then gradually, slowed by the subtle gravitational nudges of passing stars and the Milky Way's own gravitational tide, eventually settling into the vast, loosely bound cloud we now recognize as the Oort Cloud. The remarkable thing is that the Oort Cloud is completely invisible to us. No telescope has ever directly imaged it. No spacecraft has ever approached its inner edge. Its existence is inferred almost entirely from indirect evidence, specifically from the behavior of long-period comets, those icy wonders that take thousands, tens of thousands, or even millions of years to complete a single orbit around the Sun. When astronomers analyze the trajectories of these comets and trace their paths backward in time, they find that the comets come from all directions in roughly equal measure, not concentrated near the ecliptic plane. That's the fingerprint of a spherical source. A source that surrounds us on all sides. A source that matches perfectly with the theoretical model of the Oort Cloud. Every once in a while, some gravitational disturbance, a passing star, a wandering rogue planet, or the gravitational pull of the dense stellar neighborhoods our solar system passes through as it orbits. The galaxy nudges one of these distant, frozen bodies slightly. Just a tiny change in velocity is enough. The object begins a long, long fall inward, falling for thousands of years, accelerating slowly at first, and then faster and faster as it approaches the inner solar system. Eventually, it arrives near the Sun. Its ice is beginning to boil away in the solar heat, throwing off great plumes of gas and dust that form the spectacular tail we recognize as a comet. That comet you saw blazing across the sky last year might have been sleeping in the Oort Cloud since before the dinosaurs existed. Before the first fish crawled out of the ocean, possibly since before multicellular life even appeared on Earth. There is something profound in that thought. The Oort Cloud is a time capsule, a repository of the solar system's primordial ingredients, perfectly preserved in the deep freeze of space, waiting patiently in the dark for billions of years. Now push beyond the Oort Cloud and you enter a very different kind of environment. The Sun doesn't just sit passively in space, quietly burning. It's constantly exhaling. From its surface, a continuous stream of charged particles, mostly protons and electrons moving at hundreds of kilometers per second, blows outward in all directions simultaneously. This is the solar wind, and it has sculpted a protective bubble around the entire solar system that extends well above and below the ecliptic plane. This bubble is called the Heliosphere, and it is, in a very real sense, the true outer border of the Sun's direct physical influence. The heliosphere expands outward in every direction as the solar wind pushes against the gas and dust of interstellar space, and it creates a kind of cosmic force field around the solar system that shields us from a significant portion of the high-energy cosmic radiation that fills the galaxy. The heliosphere is not a perfect sphere. This is where things get particularly interesting. The solar system isn't standing still. It's moving through the galaxy at roughly 828,000 kilometers per hour, orbiting the center of the Milky Way on a journey that takes about 225 million years to complete one full circuit. As the solar system plows through the local interstellar medium at this enormous speed, the heliosphere is compressed on the leading side, the direction we're currently traveling, and stretched out into a long tail on the trailing side. The result is a shape something like an enormous cosmic comet, with a blunted nose at the front and an elongated wake streaming behind. The boundary where the solar wind starts to slow down as it collides with the incoming pressure of interstellar gas is called the termination shock. The Voyager probes crossed this boundary in the mid-2000s. Beyond the termination shock, the solar wind slows further and becomes more turbulent in a region called the heat, a chaotic mixing zone where solar particles and interstellar particles fight it out. And at the very outermost boundary, where the sun's influence finally gives way completely to the interstellar medium, is the heliopause, the true edge of the sun's direct reach. Voyager 1 crossed the heliopause in 2012, making it the first human-made object to enter interstellar space. The data it sent back confirms something remarkable. Interstellar space has a distinct character of its own. The magnetic field orientation changes. The density of particles changes. The ratio of different particle types changes. Crossing the heliopause is a genuine transition from one environment to another, like stepping from the protected air inside a building into the exposed wind of a winter storm. The heliosphere extends above and below the ecliptic plane roughly as much as it does outward toward the sides, though the complex shape means the distances aren't identical in every direction. The nose of the heliosphere, pointing in the direction of our galactic travel, is compressed to perhaps 80 to 100 astronomical units. The tail may stretch for hundreds or even thousands of O behind us. This means that, above and below the plane of the planets, the protective bubble extends for distances that dwarf even the orbit of Neptune, wrapping the entire solar system in an invisible electromagnetic embrace that has been continuously protecting the inner planets and the life on at least one of them for billions of years. Step beyond the heliopause and you're in interstellar space. But here's the thing that surprises most people. Interstellar space isn't empty, not even close. Space between the stars is filled with an incredibly thin but genuinely present mixture of gas, dust, ionized plasma, magnetic fields, and cosmic ray particles. Astronomers call this the interstellar medium, and it has structure, texture, and regional character, much like the atmosphere of a planet, just spread across vastly larger scales. The Sun is currently traveling through a specific region of the interstellar medium that astronomers have mapped and named. It's called the Local Interstellar Cloud, sometimes called the local fluff. This is a relatively warm, diffuse region of partially ionized gas, mostly hydrogen and helium, that the Sun has been passing through for somewhere between 45,000 and 150,000 years. It's denser and warmer than some of the surrounding interstellar medium, and it partially interacts with the heliosphere, influencing its shape and behavior in subtle ways. The local interstellar cloud isn't isolated either. It exists within a broader neighborhood of related clouds and filaments. When astronomers map the density and temperature of the gas surrounding our solar system using ultraviolet and X-ray observations, they can trace the outlines of these structures extending above and below the galactic plane, painting a picture of our cosmic neighborhood that is far richer and more complex than the emptiness people usually imagine when they think of deep space. All of this is constantly moving and evolving. The Sun is drifting through the local interstellar cloud at several kilometers per second relative to the surrounding gas. In perhaps 20,000 to 50,000 years, we will likely drift out of this cloud and into a different region of the interstellar medium with slightly different properties. Our heliosphere will change shape in response. The flux of cosmic rays reaching the inner solar system may shift. Whether any of this would have meaningful effects on Earth's climate or biology over geological timescale is a question scientists take seriously and are actively studying. Now expand your perspective even further. and you encounter one of the most dramatic and counterintuitive features of our cosmic neighborhood. The local bubble. And this is the part of the story where ancient catastrophe becomes the reason we exist, where we exist. The local bubble is an enormous cavity in the interstellar medium, stretching roughly 300 light-years across in most directions. Though it's not perfectly, some measurements suggest it extends over 1,000 light-years. In certain directions, the defining characteristic of the local bubble is that the density of interstellar gas inside it is dramatically lower than the surrounding regions, far more rarefied, far hotter, and dominated by very thin, extremely hot plasma. The local bubble was carved out by violence. Massive stars live fast and die in spectacular explosions called supernova. When a massive star exhausts its nuclear fuel, its core collapses in a fraction of a second, releasing an incomprehensible amount of energy that tears the star apart and blasts the surrounding interstellar medium outward at thousands of kilometers per second. A single supernova can temporarily outshine an entire galaxy, but in the region we now occupy, astronomers believe there wasn't just one supernova. Tereguere Mani estimates suggest somewhere between 14 and 20 supernova explosions occurring in this region of the galaxy over the past 10 to 20 million years. These repeated blasts, one after another, swept the interstellar gas and dust away from this region of space, creating the hollow region we now inhabit. The material that was pushed out piled up at the boundaries of the bubble, forming denser walls that are still visible in astronomical surveys today as rings of compressed gas and dust. Inside the bubble, the remnant heat from those ancient explosions is still present as extremely hot. Currently, the sun sits somewhat off-center, inside the local bubble, closer to some walls than others, drifting through the rarefied interior as it continues its long orbit around the galaxy. We are travelers passing through a vast abandoned room, one that was emptied by stellar explosions long before humanity existed. Supernovae. The local bubble shares boundaries with these neighboring structures, and the places where they meet are regions of denser, more active interstellar gas where new star formation can sometimes be triggered. The galaxy is filled with these overlapping shells and cavities, a foam-like architecture of stellar creation and destruction playing out across millions of light. All of this exists within the broader context of the Milky Way itself. And the Milky Way adds its own extraordinary dimension to the story of what's above and below us. When you look straight up at the night sky and then straight down through the Earth, you're looking perpendicular to the disk of our galaxy. The Milky Way is a spiral galaxy with a flattened disk shape. Most of its stars, gas, and dust are concentrated in this disk, which is somewhere between 1,000 and 2,000 light-years thick at our location, and about 100,000 light-years across. The sun sits roughly 2/3 of the way out from the center, in one of the galaxy's spiral arms. But the Milky Way's disk isn't perfectly flat, like a vinyl record that someone left in the sun. The outer edges of the galactic disk are slightly warped and curved, bending above the mean plane in some directions and below it in others. This warping was likely caused by the gravitational influence of the Milky Way's two large satellite galaxies, the Large and Small Magellanic Clouds, tugging on the outer disk over billions of years. The sun itself bobs up and down through the galactic plane as it orbits the galaxy. On timescales of tens of millions of years, our solar system oscillates above and below the galactic midplane like a horse on a carousel, crossing from one side to the other roughly every 30 million years or so. Right now, the sun is thought to be slightly above the galactic midplane and heading further above it, before eventually being gravitationally pulled back down and through to the other side. This slow oscillation through the galactic plane has been linked by some researchers to periodic changes in the cosmic ray flux reaching Earth, possibly influencing climate and even the frequency of mass extinction events over geological time though. These ideas remain subjects of active scientific debate. Above, and below the galactic disk itself, in all directions, perpendicular to its plane, stretches the galactic halo. The halo is a vast, roughly spherical region of much lower density that extends far beyond the visible disk. The galactic halo contains a sparse population of very old stars, remnants of the galaxy's earliest stellar generations, as well as enormous numbers of globular clusters. Dense balls of hundreds of thousands of ancient stars that orbit the galactic center in long, looping paths that carry them high above and deep below the main disk. When you look at a globular cluster through a telescope, you're looking at something that spends most of its orbital time far above or below the plane where we live, and that orbit may have remained largely unchanged for 12 or 13 billion years. But the most mysterious component of the galactic halo is also the most important: dark matter. The unknown substance that makes up roughly 85% of all the mass in the universe but emits no light and has never been directly detected is thought to be distributed in a massive halo around the Milky Way that dwarfs even the visible galactic disk in its extent. The dark matter halo shapes the gravitational architecture of the entire galaxy, holding the spinning disk together against the centrifugal forces that would otherwise fling the outer stars into intergalactic space. It extends above and below the galactic plane for hundreds of thousands of light, invisible and mysterious. The gravitational skeleton on which the entire visible galaxy is built. When you take all of this together, the Oort Cloud, the Heliosphere, the Local Interstellar Cloud, the local bubble, the galactic disk, and the dark matter halo, you start to see the solar system not as a collection of planets floating in empty space, but as a single, small node embedded within an intricate hierarchy of nested structures that extend upward and downward in scale from the smallest grain of interplanetary dust all the way to the largest structures in the observable universe. The solar system is nested inside the Oort Cloud. The Oort Cloud is nested inside the Heliosphere. The Heliosphere is nested inside the Local Interstellar Cloud. The Local Interstellar Cloud is nested inside the local bubble. The local bubble is nested inside the spiral arm of the Milky Way. The spiral arm is nested inside the galactic disk. The galactic disk is nested inside the galactic halo. The galactic halo is itself just one small island in a universe of hundreds of billions of galaxies organized into their own web of clusters, filaments, and voids stretching across 93 billion light-years of observable space. Each layer has its own physics, its own timescales, its own characteristic processes, and every single one of those layers extends above and below the ecliptic plane of our solar system, above and below the neat little diagram on the classroom poster that suggested everything interesting about our cosmic neighborhood was contained in a flat arrangement of circles and ellipses around a central yellow dot. It isn't. Not even slightly. There's something deeply humbling about this picture, but also something genuinely inspiring, because embedded within all of this, inside the Heliosphere, on the third rock from an ordinary star, sitting roughly 2/3 of the way out in the disk of an unremarkable spiral galaxy, nestled inside a cosmic cavity blasted clean by ancient stellar explosions, drifting slowly through the Local Interstellar Cloud, surrounded on all sides by the invisible mass of trillions of frozen bodies in the Oort Cloud. Life somehow happened. Not dust, microbial life, but complex life. Conscious life. Life that built telescopes and mathematics and space probes and figured out how to read the faint signals from ancient supernova embedded in the structure of the galaxy itself. That seems almost impossibly unlikely when you lay out all the layers. And yet here we are, reading the story of the cosmic architecture that surrounds us on every side, making sense of structures so vast that the human mind genuinely struggles to hold them. The fact that a mind capable of understanding the Oort Cloud can exist within it is arguably the most remarkable thing in the universe. Every time you step outside on a clear night and look up at the stars, you're looking at something familiar from a new angle. The stars above and below the plane of the Milky Way include ancient globular cluster members on their long, looping orbits. Faint glow that fills the sky at X-ray wavelengths is the hot residue of supernova explosions that cleared out the local bubble millions of years before the first humans walked the Earth. Somewhere out there, completely invisible, the Oort Cloud wraps around everything, a frozen library of the solar system's origins. Stretching a quarter of the way to the nearest star in every direction simultaneously, the solar system isn't a flat diagram. It's a living, moving, layered, cosmic structure, wrapped in shells and bubbles and fields and clouds, drifting through a galaxy that is itself embedded in something even larger. When astronomers talk about what's above and below the solar system, they're really talking about the architecture of our place in the universe. A place that turns out to be far richer, far stranger, and far more beautiful than any classroom poster ever suggested. And in the middle of all that, the Oort Cloud, the Heliosphere, the local bubble, the dark matter halo, the whole vast and impossible structure of the cosmos, is a small blue planet quietly orbiting an ordinary star, covered with creatures who somehow looked up at the sky and started asking questions. That might be the most extraordinary thing of all.